Welcome aboard, where aviation concepts become simple. From instruments to aerodynamics, we make exam prep clear and cockpit learning faster. This is StudyKwik Aviation.
Welcome to StudyKwik. In this lesson, we'll explore the principle, construction, and calibration of the airspeed indicator, ASI. We'll also learn about the relationship between indicated airspeed, IAS, calibrated airspeed, CAS, equivalent airspeed, EAS, and true airspeed, TAS. The ASI is an air pressure sensing instrument. Let's start with the basics. Air pressure. When an aircraft is stationary on the ground in still air, it experiences only the ambient atmospheric pressure, also called static pressure. Now, when the aircraft moves forward, it also experiences dynamic pressure, which depends on its speed. So, the total pressure, pitot pressure, equals static pressure, S, plus dynamic pressure, Q. Mathematically, dynamic pressure, Q, equals half rho V squared, where half rho is air density and V is the true airspeed. If we can isolate the dynamic pressure from the total pitot pressure, we can use it to show airspeed. That's exactly what the ASI does. It isolates dynamic pressure and displays it as indicated airspeed, IAS. Think of the ASI as an airtight box filled with static pressure. Inside this case, there's a thin metal capsule that receives pitot pressure, S plus Q. So capsule equals static S plus dynamic Q. Case equals static S only. Since static pressure cancels out, the capsule expands or contracts only due to dynamic pressure. This expansion and contraction are linked to the pointer, which moves across the ASI dial, showing the indicated airspeed, IAS. Now let's talk about calibration. Although dynamic pressure is proportional to speed, it also depends on air density. Air density changes with altitude, temperature, and pressure. If the air is less dense, the aircraft must fly faster to produce the same dynamic pressure. But remember, the ASI only senses dynamic pressure, not density. This means the ASI can only show the true airspeed, TAS, correctly at the density it was calibrated for. And that density is 1.225 kilograms per meter, which is the ISA, International Standard Atmosphere, sea level condition. The first error is instrument error. This happens because of imperfections in manufacturing, friction, or play in the moving parts. Even tiny flaws cause the pointer to read slightly off. Under laboratory conditions, instruments are checked against a reference instrument, and correction cards are produced. So, correcting IAS for instrument error is our first step. The next error is position error, sometimes called pressure error. This is caused by disturbed airflow around the pitot-static heads due to suction or turbulence near the aircraft structure. So, when we apply corrections for instrument error and position error, we get calibrated airspeed, CAS. In some cases, this is also called rectified airspeed, RAS. The correction card in the cockpit usually combines both instrument and position errors, so the pilot can quickly find CAS from the IAS. Now comes density error. We already know that the ASI is calibrated for sea level ISA density. At different altitudes, the air density changes, which means IAS is not TAS. This is why we use tools like the CRP5 navigation computer to correct CAS for density error. The result gives us the true airspeed, TAS. Let's pause and summarize so far. IAS plus or minus instrument and position error equals CAS. CAS plus or minus density error equals TAS. But there's one more error to consider, compressibility error. At higher speeds, especially above 300 knots, air becomes compressible when brought to rest in the pitot tube. This compression makes the sensed pressure artificially higher, which causes the ASI to overread. Near the speed of sound, the error can exceed 20 knots. So, before converting CAS to TAS at high speeds, we first apply the compressibility correction. This gives us the equivalent airspeed, EAS. EAS is the most accurate representation of dynamic pressure since it accounts for instrument error, position error, compressibility error. But in practice, we don't always need EAS to calculate TAS. Usually, CAS corrected for density error is sufficient for flight operations. Let's recap the full chain one last time. IAS, CAS, EAS, TAS. IAS corrected for instrument and position equals CAS. CAS corrected for compressibility equals EAS. CAS or EAS corrected for density equals TAS. So the ASI, though simple in appearance, is a powerful tool that tells us how fast the aircraft is moving through the air once we apply all necessary corrections. That wraps up our lesson on the airspeed indicator, ASI, its principle, construction, calibration, errors, and corrections leading to TAS. If you found this lesson helpful, don't forget to like, share, comment, and subscribe to StudyKwik for more aviation learning.